Now, on to the computer program, and the second of 10 programs that demonstrate the workings of modern computers.
Now, it's a drip-dry shirt, so we want minimum iron, that's half a spin symbol, and program E. There we are. Now, if you've used a modern washing machine, you'll know what a program is. The program consists of a preset sequence of jobs. Water in, powder in, wash, rinse, spin, and so on. You don't need to worry about it. Now, the steps a computer goes through may seem a lot more mysterious, but it's still a matter of just one thing after another.
When Vauxhall want to make a new car, first of all they have their concept, then they design it, and of course then they're faced with the problem of building it. Ideally what they would like is a machine where you feed in steel at one end, plastic, rubber, and so on, wire, and out pops a car at the other end. Unfortunately, that's not really possible. So what they have is a production line, where a set of components are brought in under the control of a set of instructions to produce a particular car. That's exactly how a computer works. Instead of components, you have numbers, characters, or words that are controlled by a set of instructions to solve a particular problem. Well, just as you may want to test a sequence of instructions in a computer program to find out if they're correct, so the instructions on the production line are checked. If car leaks, then fix it and take it back. If it doesn't leak, then continue to the next instruction. The order of the instructions, of course, is very important. Fit front-wheel drive unit in a front-wheel drive car must come before fit engine. Well, if the components are all okay and the instructions are all correct, there's one way of checking out the whole program, and that's to test the final product. And in this case, it's pretty simple. It worked.
The word program is a well-chosen one for computers. I mean, there's nothing new about the word. What it usually means is an ordered series of events at anything from an orchestral concert to a village festival. Now, to use the word for a series of instructions isn't a very big jump. But when we talk about programming computers, the word suddenly seems to take on a rather different meaning. I mean, if you think about a concert program, the list is just made up of pieces of music to play. And what you won't see is that after the interval, the London Philharmonic Orchestra will hold a bout of all-in wrestling. And even by changing the instructions, a motor car assembly line won't suddenly start turning out pottery. But a computer seems to be able to do just about anything. I mean, it can play music. It'll give you your own personal telephone directory if you wanted to. It can even draw pictures. Now, Ian McNaught-Davis, how does one machine manage to do all those different jobs?
Well, very much as your washing machine was processing your clothes, What this is doing is processing information. The information is like your clothes. It moves information around. And all it is doing to produce different things like this, it sends information to this screen, which gives it a different colour, or it would send a signal to the loudspeaker here to give different tones on the music, or it could send information out to a cassette recorder like this. And all it needs to do this is a sequence of instructions. They're relatively simple and broken down. They can move information about, they can add one number to another, and of course the secret of a computer is that they can compare one number with another and then branch or move to other sequences actions after they've done that.
And in the case of all the examples we've seen, whether it's making pictures or making music or any of the other jobs that a computer can do, it's still always the same kind of information that it's moving about inside itself.
Yes, but the program itself is broken down to these tiny little sequences, even for a colour picture like this one.
A pattern like this isn't exactly very simple, though. I mean, can you give me an example of the kind of steps a computer would go through to carry out a complicated process like this one?
Well, even a straightforward and simple job like sorting a stack of weights into order requires it to be broken down very simply for a computer. You sort the weights.
What, in weight order?
That's right. Heaviest on the right.
There's no effort in this, I don't think. No, there isn't. No.
No, that didn't stretch your credibility very much.
Not really, no.
Straight, right. Bring it back. In the order.
How would a computer do it?
What you do is start at the right-hand end.
Yes.
Pick two up.
Yes.
If the one in the right hand is lighter than the one in the left, swap.
Right, that's heavier. It's heavier. That's lighter. Swap. That's heavier. That's
right, so you've got the... Already on the first pass, you've got the lightest down at this end.
And we
Start
go
again.
all the way back to the
That's
beginning.
it.
That's correct. That's wrong. Swap.
You've done those.
That's
Those
correct.
are OK.
Those are correct. Right. And that looks about right to me. And that's how a computer would do it.
That's exactly how a computer... Because the instructions are very simple. You know, if your right hand is lighter, swap and go on to the next pair. It's a very simple piece of code for a computer to understand. And, of course, it does it extremely quickly.
Is there a real-life application of that?
Yes, there is, and I can show you that. We've got a little program here, sort. It's out of alphabetic sequence, and we're going to sort them into alphabetic order. And every time they're out of alphabetic order, we change them round.
And it's doing it by just comparing two at a time. That's all it can manage at one time.
That's
and it's
right.
seeing each pair, if one is higher up in the alphabet than the other,
Swap them over. Of course, we've slowed this down many thousands of times so we can see what exactly is going on. Of course, a computer is normally sorting millions or hundreds of thousands of items, and of course it goes a lot faster than that.
What we were looking at there, yes, was an artificially simulated, slowed-down version of what really happens. How fast does it go in
Well,
fact?
that one was slowed down thousands of times, but I think we can give you an idea of how fast it goes.
Yes. I mean, it's less than a second.
And it's extremely quick, and that's the real whole point of a computer, taking very, very simple instructions, but being able to do them incredibly quickly. It seems laborious for a human being. For a computer, it's very simple.
Right.
In its own way, a computer goes about its job just like a very finely tuned piece of machinery. In a beautiful piece of machinery like this, the individual parts, the wheels, the levers, the gears and the cranks, are all quite easy to understand in themselves. But it's the way they go together that makes the whole thing seem complicated and produce a result that you might not expect just by looking at it. The violano works from music on a roll of paper punched with holes. It's a simple way of storing information. But it wasn't the first machine to use this system. To trace the beginnings of punch paper or cards, we have to go a lot further back in history and look at a more down-to-earth device. Well, I think after a few 12-hour shifts, I'd really get to know how to operate this machine. It's the famous Jacquard loom, and even though it was invented nearly 200 years ago, some of the principles in it are still in use in modern computers today. Using this machine, it's possible to produce any pattern that you like, even a beautiful pattern like this. All that it means is that a different combination of these warp threads have to be lifted every time the shuttle goes across, and we gradually progress down through the cloth. Well, one way of doing it, of lifting these different combinations, was to have a small boy sat at the top of the loom, and every time the shuttle went across, he would pull up a different combination of these threads. Of course, that was fairly laborious and subject to errors, but it did work and was used. But that's where Jacquard made his breakthrough. He devised one method of getting information into this machine which would do exactly that job. And that information was stored on these punch cards. It was, in essence, a very simple idea. Where there was a hole, a thread would be lifted. Where there was no hole, it wouldn't be lifted. So each time a card went through, a different combination of threads would be lifted and the pattern created.
Weaving is just one example of a binary or two-way system. Now, the point with weaving is that each warp thread can be either up or down, but with even such a limited choice for each thread, the number of patterns which can be made is almost infinite. Let me show you how it works. With one warp thread, either up or down, the weft thread crossing it can either go under or over it, two possible routes. With two warp threads, the weft can go one of four different ways: under both, under one and over the other, over the first one and under the other, or over both. Every time you add a warp thread, the number of possible combinations doubles, so that with 8 threads, and we've had to lay them out in 4 columns because the possibilities are so many, the weft actually has a choice of 256 possible routes across them. And this will progressively draw them in. Now, Mac, isn't that basically how a computer works?
Well, instead of threads, of course, they're electrical ons or offs. I quite like to think of them as pots, which either have electricity in them or are empty, rather like these jars on this shelf, some of which have things in them, some of which are empty. And in this particular computer, they're grouped in 8s, so you can get the 256 combinations.
And each combination represents what, a different number?
Well, a number or a special symbol or an alphabetic character or even a command. For example, this one, empty, empty, full, empty, 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 represents a left bracket. And this one, we think of them as 00110110, represents number 6. And this one represents A, which could be just the letter A, or it could be a command, for example, A meaning add, to add 2 numbers together.
Right, and an ordinary personal computer like this one would use all 256 of those?
Yes, all 256.
Right. Well, giving commands in the form of binary patterns is actually surprisingly something quite familiar to us, as our reporter Gill Nevill has been finding out.
As you slow down for traffic lights, it's probably never crossed your mind that what you're doing is obeying an instruction in binary code. If you've thought of the nature of traffic lights at all, and why should you have done, you've probably thought of them as a simple colour code. Red means stop, green means go, and so on. But there's another way of looking at traffic lights that means that you can understand the signals even if you're completely colourblind. Each of the lights has a definite position and can be either on or off. And according to the different combinations of on and offs, so the meaning changes.
The 3 lights can be combined in 8 different ways, but of those combinations, only 4 mean anything to drivers. If the top light's on, you stop. If the top 2 lights are on, you get ready to go, and when the bottom one's on, you go. And the cycle continues, with the middle light meaning prepare to stop when the top light shows again.
Computers also work in binary, so not surprisingly, they can be used to control whole networks of traffic lights, as unlikely as it may seem as you struggle through the traffic. All these traffic lights on every street corner are precisely synchronized to get the majority of cars to their destinations as quickly as possible. And if things seem bad, well, they'd be a whole lot worse without that computer in control.
In London, the traffic light system's controlled from New Scotland Yard.
We're looking at the cameras at the moment, which are covering the Euston Road from the Euston Underpass right over to the Pentonville Road. The computer is programmed to bring in the maximum eastbound or into-town bias for the morning peak, and then it changes off to the off-peak at about 10 o'clock, and then the evening peak at 3 o'clock, and so on, right through the 24 hours of the day.
From his position at the console, the operator can change the pre-programmed sequences of lights to speed the flow. If there's a heavy build-up of traffic, he can switch the computer to a contingency plan designed to increase flow in one direction.
The plan which is put in for this time of day isn't sufficient for that, so I could put in a contingency which would increase the eastbound flow. In this case, it's Group 8, which controls the whole of the east side of Euston Road. By putting in the maximum eastbound plan, which gives it 7 or 8 seconds on all the eastbound junctions, it should clear that backlog.
Altering the sequence at any one set of traffic lights has a marked effect on all the roads radiating from it, and the timing of the other lights in the area has to be adjusted accordingly. It takes a computer to cope with a problem of such complexity and keep the traffic moving.
Now, obviously, keeping London's traffic moving is an immensely difficult task and something that a computer is well suited to do. But it's still only just doing one thing after another, isn't it, Mac?
Yes, they can only do a relatively limited number of things, and in fact the instructions can only be put together in a limited number of ways, in fact only 3 ways. They can be executed or followed in a sequence, just done one after the other from beginning to end, or you can execute a sequence of instructions and do it again and again a certain number of times. And then the exciting bit, which makes a computer seem to have some sort of intelligence, it can test whether a condition is true or false, and as a result of that test, can do either one set of instructions or a different set of instructions.
Beginning to sound a little bit like cooking, in that there only are a very limited number of processes you can inflict on a set of ingredients. You can boil, bake, or roast, or fry them. And a limited number of ingredients you can do it with, of course. But by combining the instructions in different ways, there's no limit to the number of dishes you can make. Take making mayonnaise, for example. The first thing you do is to get an egg, a container of oil, and a bowl to mix the mayonnaise in. Then you put the egg yolk in the bowl, add salt, pepper, and a little vinegar, and mix them all together.
And those instructions are simply stepped through one at a time.
Then you drip the oil into the egg, a drop at a time, and whisk the mixture.
Now you're performing that group of processes over and over again. Drip, whisk, look at the oil. Drip, whisk, look at the oil. Until the oil is finished.
If the mayonnaise curdles, you put in another egg yolk and go back to dripping in oil again.
And those instructions are only to be performed if it curdles. Otherwise, the mayonnaise is finished. And you can eat it.
That's fine when the instructions are about cooking. But what about the instructions on a computer?
Well, this is a program we have stored in the machine. In other words, it's a list of instructions.
This has been pre-done. This is what we did.
Yes,
okay.
Just a couple of lines of a program. In other words, a list of instructions that will tell the machine what exactly to do. And you'll see they're numbered, so it tells the machine in which order to do them. It could have been 1 and 2, but you usually number them 10, 20, because you might miss one out, forget a line, you want to slip a line in there afterwards.
So you could say 11, 12, 13, 14,
yes, you could do. Yes, certainly. And the first one is print. And inverted commas. It's like, I always think of it like a conversation in a book. If you put something in inverted commas, it means it's conversation. So that tells the computer to actually print "Where is the Vatican?" ? On the screen when you run it.
Okay. So when you run the program, that's what you get. That's all you get is "Where's the Vatican?"
For that one line, that's right.
Yeah.
So that's fairly straightforward. Print will always do that. It will print on the screen whatever you put inside these quotation marks. And this is That's basic. That's the language that we're using on this particular computer.
OK, what about the second line? I don't
Well,
understand at all.
That's much more complicated. Again, that's a basic command, input. And what it's saying is, I'm asking you to input something into the computer. It's calling for input, which is put in on this keyboard.
So that's the computer talking to me?
Effectively, it will do. And I'll show you how it runs in a minute.
All right.
Now, when you input something, it needs to know where to locate it in its memory. And we're calling this here city string, which means it's expecting you to input some alphabetic characters. Where's the Vatican? It's going to be a word you're going to put in.
That's what that dollar sign means.
And that's what that curious little nasty
Again,
dollar sign.
that's something that's part of this basic language.
That's
rather
right,
than,
yes.
Yeah. Okay.
So if we run that, and we can get the computer to actually run through those two instructions and try it out. So you just type run.
You type run?
Yeah, so
and that's
simple
all
as
you
that.
need to do, all right.
And return. So there it is. Where's the Vatican?
Yeah.
And it gives you a little question mark saying, what are you going to put in? So it's expecting you now to put in a word.
Shall I type?
Now, I don't think we should do that just yet, because I'd like to look at the programme, to look at it a little bit further. So we should escape from the programme. There's a little key here. It's like escape from Stalag, whatever it is, and bang.
Yeah.
And that gives the escape from where we were, which was line 20.
Right, so we've interrupted the
We've interrupted the programme. Now, I think we should list it, and we can just... Another basic command is just type list, which will list the programme for us.
Press return again.
Return again.
Okay.
And that's the whole programme, the first two. And on line 30, we've put this... The sort of statement we did at the end of the Mayo sequence, which was, you know, if the Mayo's OK, eat it. If it isn't, start again and put some more egg yolk in. This one, we've said if what you've typed in is not equal, that's horrid sign means not equal to Rome, then print wrong.
OK. So let me just go over this again. When you run the programme, you're going to get the question, as we did, where is the Vatican? And then you're going to get a question mark. And if you type an answer which isn't the correct answer, which isn't Rome, then it'll say wrong.
That's correct.
Okay.
Yes. So we can write a line. Would you like to write another line to say... I think we could put in a line which would say what happens...
No, I've got to type a number, haven't I?
Yes.
40, I guess.
You could type any number as long as it's bigger than 30.
Yeah.
I'm going to let you test this out. You're going to have to work this one out for yourself.
Right. Well, presumably you have to say if, this funny business, if city dollar is Rome, then print correct or
that's right.
right or
well, that's
something.
it, yes.
Right.
Except instead of is, type equals.
OK. Where is it? There it is. Equals.
Equals.
In quotation marks, yes. End quotation marks. Then P-I-T.
Well, it looks OK, and...
Now what?
Let's see if it works.
So, run.
Run again.
Where is the Vatican? London. What do I do now? I mean, it hasn't responded.
Return. Always after the line.
Wrong.
Wrong.
That works. That works, all right.
Run it again.
Let's try the right answer. I hope I have got the right answer. All right.
So it was a very simple little program, but it gives you that warm feeling of having done something and understood something.
Absolutely.
And it is the basis of many programs. That if-then instruction is the real thing that separates a computer from a straightforward calculator. It can make little decisions within itself.
I can also understand your feelings when you talk about the sense of gratification and the pleasure you get, even from a very simple thing like that. You know, it's a very good feeling when it goes right, isn't it?
It certainly is.
Yeah. So even at this simple level, the computer can be made to do something that seems almost intelligent. Of course, I know the Vatican is in Rome, but a school child might not. A series of questions from the computer, programmed in precisely the same way, could make an interesting and educational quiz.